Right, so this is going to be the first of two videos on titrations. In this one, I'm just going to focus on the actual experimental method itself, with a particular emphasis on things that you can do wrong. In the exam, they tend to ask questions about the accuracy of titrations, and they can be quite tricky and do involve a proper understanding of the titration and how it works to be able to answer. And in the second of the two videos, I'll focus on the calculations that come up around titrations. So what I've got here is an acid, hydrochloric acid, and I'm telling you that the concentration is unknown. To work out the concentration of this acid, we're going to titrate it against an alkali. I've chosen NaOH, but you could use any alkali. And I've written the equation for this reaction, and I form the salt, NaCl, and I form water. And you can see from my balanced equation that the ratio between the alkali I've chosen and the acid is 1:1. So this would mean if I had 1 mole of HCl in this solution, that it would take 1 mole of NaOH to neutralize it. And same if I had half a mole, it would take half a mole to neutralize it. So in order for this to work, whatever I've decided to titrate my unknown against, I need to have a standard solution of that. And by standard solution, I just mean a solution where the concentration is accurately known. And to ensure you know that concentration accurately, you're going to make it up yourself. So let's say, for example, I'm going to make up sodium hydroxide and I want it to have a 0.1 mole per decimeter cubed. That's the concentration I want it to have. So decimeters cubed is the same as a litre, so 1 decimeters cubed equals 1 litre. And typically when we're making up solutions, you don't make up a full decimeters cubed, you typically make up 250 centimeters cubed, or 0.25 decimeters cubed. Which is a quarter of the size, because your typical volumetric flask is 0.25 decimeters cubed, or 250 centimeters cubed. So if I'm making up a solution with the volume is a quarter of the size, that means I'm going to be only adding a quarter of the number of moles. So I'd want that number of moles if I had a full decimeter cubed, but when I only have a quarter of a decimeter cubed, I'm going to have a quarter of the number of moles. So now I know how many moles I want to add. I need to work out the mass. So I know moles. I work out the formula mass of NaOH, so it's just going to be 23 plus 16 plus 1. It works out as 40. And I multiply the number of moles by the formula mass, and it works out as 1 gram. So if I want to make up a standard solution of NaOH with this concentration, I'm going to need to weigh out 1 gram of sodium hydroxide. And I weigh out my gram of sodium hydroxide, and then I transfer that gram to a volumetric flask. We always use volumetric flasks to make up standard solutions. They can ask you a few practical questions about how you would transfer the sodium hydroxide to make sure that all of it got transferred into the flask. So you'll weigh it out on a little weigh boat. You'll tip the solid into the flask, but then you can get a little water bottle and rinse down the weigh boat with water, and then tip the rinsings into the flask. You can also use your water bottle to rinse down the side of the flask and make sure that all of those rinsings add to the bottom. Once you've ensured that you have definitely added all of that solid into the flask, you will fill it up to the mark with deionized water, making sure that the top of the meniscus sits in the line. You'll put in your stopper, you'll invert it a couple of times, and then you've got your standard solution, a solution where you accurately know the concentration. And once you've got your standard solution of sodium hydroxide, you're going to... you can actually do two things here. You can either add your standard solution to the burette, or you can add your standard solution to the conical flask. It doesn't actually matter which way around you do it. In this case, I'm going to say I'm adding my standard solution to the conical flask. And to do this, I'm going to need to use a pipette. And pipettes are pieces of glassware that will accurately measure out 1 volume, in this case 25 centimeters cubed. So I use my pipette and I add my sodium hydroxide to my conical flask. And I can work out exactly how many moles of sodium hydroxide I've added to my conical flask. Because I know my concentration, because I'm just after making this up, and I know the volume that I've just added using my pipette, I can work out exactly how many moles of sodium hydroxide are now in my conical flask. And then what I'm going to do is I'm going to take my unknown solution, which in this case is the hydrochloric acid. I'm going to put my hydrochloric acid into the burette, and I'm going to titration it against my sodium hydroxide. Now, as I said a second ago, I could do this the other way around. I could have my sodium hydroxide in the burette and my unknown in the conical flask. It doesn't actually matter. But I can use the ratio that I had from my balanced chemical equation, and I know I've added 2.5 moles of sodium hydroxide to my conical flask. And because it's a 1:1 ratio, as soon as I add an equal number of moles of the acid to my conical flask, that's when I'm going to see my colour change, when exactly this number of moles is added. And what I would need to do is I'd need to repeat the titration a number of times in order to get concordant results, so volumes that are within 0.1 centimetres cubed. But let's just say once I've done that, I've got my concordant results and I've got the mean, that the volume of HCl required, let's just say it's 0.027 decimeters cubed. So that's the volume of HCl required. So that volume must have this number of moles in it. Okay, I know I'm going to see the color change when I've got this number of moles of HCl added, and that corresponds to this volume, because that's the volume that caused the change. And then I can take those two values and I can use them to work out what my concentration will be. So I'll take my value for moles, I'll divide by my value for volume, and I'll work out that my concentration is 0.092, okay? And that is the concentration of my hydrochloric acid. I'm going to go back to these calculations, as I said in the next video. There's just a few things I want to point out in terms of the accuracy of the titrations. So one of the things that the kind of more basic questions they can ask you is just in terms of the glassware itself. So they can give you a method and they ask you what the student did wrong. If they're talking about making a standard solution, the glassware should always be a volumetric flask. You'd never make one up in a beaker or a conical flask because they don't measure volume accurately enough. In terms of whatever you're adding to the conical flask, you have to use a pipette, again using a beaker, using a graduated cylinder, that's not accurate enough. And then obviously you've got your burette. So just basic questions on glassware and knowing the pieces of glassware to use. They can also ask you a few questions about the titer itself. So when I'm talking about the titer, I'm talking about this, the volume that you've added from your burette. So again, you're going to do this a couple of times and you're going to get the average, but whatever you're adding from the burette, that's your titer. And they can ask you questions about, sometimes the titer is too large, and sometimes the titer is too small, or smaller than expected, or smaller than everyone else in the group who did it. And they can ask you to suggest reasons why. So the first thing we're going to look at is reasons that would cause the titer to be too large. So by that I mean you've added more from the burette than everyone else has, okay? And again, it doesn't matter what's in your burette, whether it's the acid or the alkali, whether it's the unknown concentration or your standard solution, these answers will apply regardless of what's in your burette. But if you've got a large titer and you've added more than everyone else, we need to look at the reasons why. So if you're adding more than everyone else, it's going to mean one of two things. If you had to add more to see that color change, you have either got less moles in burette than you're supposed to, or you have got more moles in your conical flask than you are supposed to. That's what would result in a larger titer. So if we look at the first one, okay, what would cause you to have less moles in the burette than you're supposed to, okay? And one of the common things that would cause you to have less moles in your burette would be if you rinsed your burette with water and left that water there. So if you rinsed burette with water. So what you're supposed to do when you're filling the burette is you're supposed to initially open the tap. You can rinse it through with whatever solution it's about to contain. So in this one, I know I'm going to have it filled with HCl. So I should have the tap open at the start, rinse it through with HCl so that the burette is coated with the solution it's about to contain. If you rinse it through with water and you've got lots of droplets of water within your burette, when you close the tap and then start adding your HCl, you're not going to be able to get the full volume of HCl in in there because you've already got droplets of water taking up space, and that water will dilute your HCl. So it's really important that if you've rinsed your burette with water, that you then rinse it through with the solution it's about to contain. If you don't, you're going to end up with less moles in burette than intended, and you're going to end up with a larger titer. Another thing that you could have in there would be an air bubble. So when you're filling the burette, if you end up with a big air bubble, then again, you're getting less volume into the burette than you're supposed to. And when you open the tap and just say you think you've added 20, well, you haven't actually added 20 centimeters cubed because a part of that volume had a big air bubble in it. So you're adding less than what you're expecting. And both of those will give you a larger titer than you're expecting. The other thing here would be that you have more moles in your conical flask than you intended. So whatever you've measured in your conical flask, that was too concentrated. Again, I guess an error with that would be if you used your pipette incorrectly. If you went above the 25 centimeter cubed line, you would be adding more to that conical flask than you intended. Another thing here, when you made up the volumetric flask in the first place, if you didn't bring the water right up to the line, then you've got a more concentrated solution than expected. So that will cause you to have more moles in your conical flask if what's in your conical flask was your standard solution. So that would result in more moles in your conical flask, I guess, if you went beyond the line with your pipette. Would give you more moles in your conical flask. If we look at you getting a smaller titer, okay, so in other words, it didn't require as big a volume from your burette. So what's going on there? So if it doesn't require as much from your burette, then you likely have more moles in your burette than you're supposed to. So what's in your burette is more concentrated than everyone else's. Or if you're having a smaller titer, it's because you've got less moles in your conical flask. In other words, there's less moles in your conical flask, so not as much is required from the burette to neutralize it. So again, if we're looking at more moles in the burette, what could cause that? Again, for more moles, it would just be a case of that you haven't used your measuring equipment properly. You maybe have gone beyond zero at the start, so you've got a greater volume in there than you should. Or again, if what was in your burette came from your volumetric flask, if you put your standard solution straight into burette, again, if you hadn't filled the water to the line and it was concentrated and you added that to your burette, you'd have more moles in your burette than you're supposed to. But this one here is the most kind of relevant, the less moles in the conical flask. This one comes up quite a bit. So if we look up here, less moles in your conical flask, in order to have the correct number of moles in your conical flask, you have to use your pipette properly. And just like the burette that we talked about before, it's okay to rinse your pipette with water first, but then you have to rinse it with the solution it's about to contain. If you've got your pipette with lots of droplets of water in there, and then you try and measure out 25 centimeters cubed, that water that remains in the pipette is just going to dilute your alkali or dilute your acid, and you're not going to end up transferring the correct number of moles to your conical flask. So again, if you've rinsed your pipette with water, that is going to mean you're transferring less moles than you want to the conical flask. The one that they sometimes throw in as a kind of distractor is they'll say, what if there's water left over in the conical flask? And students see that and they think, oh, if there's water in the conical flask already, then you've got a more dilute solution in the conical flask, therefore there's less moles than expected, and you're going to have a smaller titer. That's not the case, okay? Even if there is some water in this conical flask, as long as you have got your concentration accurate from your standard solution, and as long as you've used your pipette correctly, then you are transferring the correct number of moles. If your concentration's accurate and your volume's accurate, the number of moles you are transferring is accurate. And as long as I've got 2.5 by 10 to the minus 3 moles here in my conical flask, then this is the volume of acid that's going to be required to neutralize that number of moles. Remember, when I'm doing my calculation down here and the concentration I plug in, I'm plugging in this value here, that's the concentration from my volumetric flask. It's not the concentration from my conical flask. So yes, if there was water in here, the concentration in the conical flask would be slightly different, but you still have the correct number of moles in your conical flask. And if I've got 2.5 by 10 to the minus 3 in there, then that is going to be the number of moles of HCl that will neutralize it, even if that number of moles is swimming around in a greater volume of water. It's not going to impact. And that's a common distractor. Okay, so water being in the conical flask will not make your titer smaller. As long as you've used your pipette correctly, you will still have the same titer. Another kind of distractor with these questions is they give, they said with the burette, you obviously have to take 2 readings, an initial and a final. And they said a student read from the top of the meniscus both times. Well, in that case, you're supposed to read from the bottom of the meniscus, but because he's read from the top both times, his 2 mistakes have cancelled each other out, and the volume he'd calculate would still be the same as if you read from the bottom of the meniscus both times. There are 2 multiple choice questions on this that came up, which we have done in class, but I guess just have a look at that first one. Press pause, have a look at what you think it might be. And then press play when you're ready to see the answer. Okay, so the answer is D. I'll just quickly run through why that is. They tell you that the standard solution has gone into the burette. So the thing that you've just made up in the volumetric flask, that's what's in the burette. And they're saying that the titer is larger than it should be. In other words, you needed to add more from the burette than what other people did. And if you're adding more from the burette, that means that you must have less moles in the burette than you're supposed to, or you have more moles in the conical flask than you are supposed to. So the first one here, water is added to completely fill the volumetric flask rather than the graduation line. So if you're adding too much water, that is going to make your standard solution more dilute. We put the standard solution into the burette. So if it was more dilute, then you would have less moles in there than you're supposed to, which fits. Okay, so D is going to be correct. 1 is going to be correct. The next one, the conical flask is washed out with water before carrying out each titration. Again, that's not going to affect the number of moles at all. It's definitely not going to give you more moles in the conical flask, so 2 is definitely going to be wrong. And if you look at 3, the pipette is washed out with water before carrying out each titration. Again, if I'm washing the pipette with water, that affects what's in my conical flask, and it would give me less moles in my conical flask. I would need to have more moles for a bigger titer. So the answer is just going to be 1, which makes it D. This next question here is similar. So just pause and have a go at that one. So here in this one, it's saying smaller titer, so you're adding less from the burette than you would expected. The first thing here, they're taking the readings from the top. Again, I said those mistakes, if you're doing consistent label, effectively cancel out. Conical flask is rinsed with water. I know, again, that seems like it might be the right answer, but as long as you use your pipette correctly and you've used your volumetric flask correctly and you transfer the correct number of moles to that conical flask, it doesn't matter if there's already water in there. An air bubble is released from the jet of the burette. If they have an air bubble in there, you will be adding you'll end up adding more from the burette, not less. If some of the volume is taken up with just air, then you'll have to add extra in order to neutralize. Whereas here you've got a smaller titer, that would result in a larger titer. So it's this one here. D is going to be the answer. The pipette is rinsed with water. You end up with a smaller titer, because what's in your conical flask is more dilute than it should be. You're adding less moles to the conical flask than intended because you've got water in the pipette and you don't end up adding as much as you should. The next question here, actually, this comes up all the time, percentage uncertainty. And there's a general formula for percentage uncertainty. And it's just the uncertainty reading, which is always given to you in the question, and here it's going to be 0.05. and then you divide it by the titer. So your initial reading is 5, your final reading is 24.95. So you're just going to work out what the actual titer was. So it's 24.95 minus 5, so 19.95. Then you multiply by 100 because it's a percentage, and then you have to multiply it by 2, but only when you're doing this for a burette. And the reason I times it by 2 is I have to take 2 readings with the burette, an initial and a final, because I have to do the reading twice, and my percentage of uncertainty has to be times by 2. So I work that out and I get, well, whatever the answer is. If I was doing this with a pipette instead, I would do exactly the same thing, but I wouldn't multiply by 2. In a pipette, I only take 1 reading, not 2, so there's no need to multiply by 2. The other thing to note with these questions is here it's pretty obvious. I just work out what the titer is, and that's the volume I'm going to plug in down here. Often they give you data where you've got multiple titers. I'll find one. Yeah, something like this. I'd have multiple titers, titration 1, 2, and 3. If they ask you for the percentage uncertainty and they don't specify which titration to use, you can use any of the 3. You don't have to use the mean, you don't have to just use the concordance, you can use any of the 3, and you'll see in the mark scheme at the back, unless they've specified which one they want you to use, they'll accept any of the volumes from any of the titrations. Sorry, just 1 or 2 other things I want to point out in terms of titrations. In terms of concordant titers, okay, just make sure you're saying that it's within 0.1 or 0.05. That's your concordant titer. Standard solutions that are having an accurate, sorry, the concentration is accurately known. When you are recording titers, you have to record to 2 decimal places. Even in this case here, it's 27. If you're at 27, it's wrong. It's 27.00. So make sure you watch for that. When you calculate your titers then, make sure you're only taking the concordant results when you're actually calculating your mean. Other things to point out, the rest of them are calculation questions, which I'm going to do in a separate video. Yeah. The rest of them are mostly calculations. Oh, this is another percentage uncertainty question. So it says that in the titrations, they measured volumes of the pipette and a burette. With the pipette, they give you the percentage uncertainty, 0.04. You have to go back and look through the question and see what volume is actually measured with the pipette, and you'll see that it's 25 centimeters cubed. So you'll put your 25 there, and then you times by 100. You don't need to multiply by 2 for the pipette. And then for the burette, you've got your 0.05 as your uncertainty. You have to scroll back into your question to find out what the measurement was. And here they give you a table, and you can use any of these titers and plug that into your equation here, because they haven't specified which titration you have to use. You multiply it by 100, and then for the burette, you multiply it by 2 because you're taking 2 readings. These are all, yeah, okay. Beyond that, the questions tend to get a bit repetitive. Yeah, so the next video I'll just go through how to do the titrations calculations, because they come up all the time.